Okay, let's get started. Good morning. That was bad. Good morning. That's much better. We're doing exciting stuff today, so we should be excited. Okay, so what are we doing today? We're talking about series. Finally. Okay, so we're going to be doing a lot of different stuff related to series. We're just going to be doing a little bit of introduction as to what a series is, and then two very important series that we will see over and over again later in this chapter. So first of all, remember last time we talked about sequence. And you remember that a sequence is just a list of numbers in a specific order. And often we write it between curly brackets, the name of the series, and then the index, which tells you which term in the series that number is, in a sequence. A series is kind of like that. But instead of just listing the numbers, we add them together. So a series is a sum of numbers. So for example, a series might look like A1 plus A2 plus A3 plus A4 plus ... right? And very often we see this written in summation notation. And we'll be dealing with infinite series. So the series doesn't end. We're adding up an infinitely many list of numbers. Kind of like an infinite sequence with a very long list here. We're just adding them up together. So that's how these things are similar, but at the same time, fundamentally different. Okay, so another example of a series. The basic idea of dealing with these things is very much like dealing with sequences. You look at the numbers you got, you look for some kind of pattern that's involved here. So notice what's going on here. This is 1 over 3 to the first. That's 1 over 3 to the second. That's 1 over 3 to the third, fourth, and so on, right? So in the summation notation, we would write it this way. Okay? So I start adding at n is equal to 1. And when n is equal to 1, I get 1 over 3 to the first, and that's this one right here. Then I add when n is equal to 2, 1 over 3 squared. That's 1 over 9. Then I move on to n is equal to 3, 1 over 3 cubed, n equal to 4, so on and so on. And I never end that. I just keep going. Okay, does that make sense how this thing came out? Yep. Like I say, you look for a pattern and then you make a condensed form. The sum of a series is the number you get when all terms are added. And for an infinite series, that means adding up infinitely many numbers. Now, upon first, this may seem a little counterintuitive. How can you add infinitely many numbers and still get a fixed number? But actually, you can, and it happens quite often. For example, take the number pi. We know this is an irrational number. And of course, the digits continue forever. Now, if you think about how we get this number, we get this by starting with a 3, and then we add to it 1 over 10, right? That's my 0.1. And then my 0.04 is 4 over 10 squared. And my next one is 1 over 10 cubed. And then 5 over 10 to the 4th, plus 9, 10 to the 5th, plus so on. Right? So what I got here is pi expressed as a series. And we know pi is a finite number. It's got so many decimal places, but it's a finite number. So this means that if I could actually add all of these up, I actually get a finite number. And that's one example of an infinite series that when you are able to add all of these numbers together, you get a finite number. And that's quite important with series. Series that when you add them together, you get an ordinary number. So how can we tell if a series has a sum? We can look at the behavior of the partial sums of the series. So when we write S with a subscript n, this means that this is the sum of the first n terms. Okay, so that's called the nth partial sum. So S1, for example, is just the first term, right? So S1 is A1. S2 is A1 plus A2. That's the sum of first two terms in the series. S3 is A1 plus A2 plus A3, and so on. Okay? So Sn is the first n of these. Here's an interesting to note. If I take S, the nth partial sum, minus the n minus 1 partial sum, for example, S3 minus S2, what do I get? Look at the example here. I get A3. So in general, what would I get? AN, right? Yeah. This result will actually come in handy later. So make a note of that. We'll come back to it. Not bad. The series converges. So here's that word again. If the sequence of the partial sums if the sequence of partial sums converges. Okay, so now we saw this last Friday. What does it mean when you say a sequence converges? What has to happen? The what? Okay, the limit, right? There's a limit to the sequence, yeah. So this means the limit as n goes to infinity of the nth term in that sequence must approach an ordinary number, not infinity and not minus infinity. Okay, so that's a definition of a convergent sequence. The last term has to approach something, some number. And what this means in terms of the sequence then is that if I were able to add all of these things up, so this is my S sub n, right? And if I take this n to infinity, I actually get a number. And it's not plus or minus infinity. So this is saying that when I add all of these terms up, I get a finite number. That's what this first definition tells you. So now I want you to etch this in your mind now. When we say a series converges, it means that it has a finite sum. Okay? You're going to have to use that concept later when the series gets more complicated. Just keep in mind that when we say it converges, it means that there is a sum. We may not be able to find that sum all the time. Sometimes we have to approximate that. But the important thing is it does have a sum. Once again, my pi example. Right? I add all of these things up. In the end, I get a pi. And that's a finite fixed number. So this infinite series has a sum. And this infinite series, therefore, converges. Does that make sense? Converges to what? To pi, right? Okay, so that's the simplest way to see if a series converges, to study the behavior of the sequence of partial sums. Let's look at the example one example I showed you earlier. That series we saw earlier. Let's find out if this series converges. Okay, on the last slide, we saw that this thing converges if the partial sums look like they're going somewhere. So that's what we will do here. I'm going to make a table here of the partial sums. Okay, the first partial sum is simply the first term, and that's 1 over 3. 0.3333, and so on, right? Then the second partial sum is the sum of the first two terms, 1 over 3 plus 1 over 9. And I calculated these beforehand. It's about 0.444 repeating. The third partial sum is the sum of the first three terms, 1 over 3 plus 1 over 9 1 over 27. And it's roughly that. Okay, now you get the idea. We're just going to look at the numbers. The sum of the first 4 terms give me that. Sum of the first 5. First 6. The first 7. The first 8. We're going to go up to 10, and then we'll stop there. Because it is starting to settle down to something. Okay, so I made a table of the first 10 partial sums. Do this with a calculator, of course. And as you can see, these numbers started kind of low and then jumped up again. But after a little while, it seems to be settling down, right? So based on the behavior of these partial sums, and based on the definition of a convergent series, what is your conclusion here? Yes, it does. Because these numbers look like they're approaching some kind of limit. Some kind of limit. In fact, can we estimate what the limit is? About 1/2? Right. This method is not going to tell us exactly what the limit is, but we can look at the behavior here and then kind of estimate what the limit is. And it looks like 1/2. If you were to graph what we just saw, then you'll see something like this. So I'm plotting the partial sums. Okay? So you see, started here, move up, move up, move up, and eventually kind of settling around 0.5. It looks like a horizontal asymptote. Which means that it's got some kind of limit, and because the number is settling down to something, this is a convergent series. It says that as you add more and more terms together, eventually the sum approaches about 0.5. Doesn't seem to want to go over that. In fact, wants to go closer and closer to 0.5. So this is a very typical graph of a convergent series. If you were to graph the pi series I showed you earlier, you'll see about the same thing here. The beginning may be a little bit wild, but then eventually it'll settle down, and settle down around 3.14159, there and about. Questions? Okay, good. Let's look at another one. So this series will show up over and over again in this chapter. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1 over 6, 1 over 7, blah, blah, blah. And in the summation notation is 1 over n. This is called the harmonic series. It's got a pretty nice name to it, harmonic series. It's based on the concept of overtones in music. So if you have a stringed instrument, you vibrate that string, you hear a tone. You make the string half as long by putting your finger on the fretboard, for example, and then 1/2 gives you another tone, 1/3 gives you another tone, and so on and so on. So this is based on terminology from music. But remember this name here and that series. This will come back later on. Okay, and we'll make the same table here, the first 10 or so partial sums. N equal to 1 again is just the first term, 1. N is equal to 2 is the first 2, and that's 1.5. Third partial sum, $1.8333. The fourth, fifth, sixth, seventh, eighth, ninth, 10th. Okay, normally you can make a decision very quickly after maybe 5 or 6. We go 10 just to be super clear about it. Okay, once again, based on the definition of a convergent series, we're asking, does the sequence converge? Does it look like these numbers are trying to get to somewhere and staying there? What do you think? Doesn't look like it, does it? In fact, if I do 11, this is probably going to go over 3. If I go 12, it's probably going to go 3.1 or so. If I go to 100, this is probably going to be somewhere near 20 or so, based on the progression here. Okay, so the answer is no. Right? The sequence of partial sums does not converge. So the series diverges. And that means that the series has no finite sum. The number, as I add them, is just going to get bigger and bigger and bigger. It is not going anywhere, and certainly not going to settle down anywhere. It has no finite sum. It's a very nice looking series, very ordinary, very predictable, got a nice name, but it doesn't behave. And look at the graph and compare to the last one. Okay, so this is a typical converging series. It's got some kind of horizontal asymptote. Here's the harmonic series. it is slowing, the growth seems to be slowing down, but it doesn't appear to be settling down. Okay? There's some series that actually will converge, but look kind of like this. Some series converge very slowly, but most of the series we deal with and in common applications converge quickly. So very often it will settle down quickly for a convergent series and keeps increasing or decreasing for a divergent series. Questions? Nope? Okay, good. Let's look at the this series we looked at earlier. Actually, we look at a series 1 over 3 plus 1 over 9, so on and so on earlier. I added 1 to the beginning of it. And we saw earlier that without a 1, this series converges, right? Without a 1 in front, this has a finite sum, about 0.5. So now, the question is, if I add 1 to it, is it going to converge or diverge? Does adding the 1 to it make any difference? Why not? Right. Converge means that this thing here has a finite sum, right? If all of these numbers added together is a finite number, by adding one finite number to that, it's another finite number. So therefore, this does not affect the convergence. Make sense? So this converges. So 1 plus all of that stuff also converges, because 1 plus finite number is another finite number. Another example, we know pi converges, and I can write pi in a big series. 1 plus pi is still a finite number, right? All these finite numbers added together is another finite number. So that's another concept we'll need later on. By adding something to a convergent series, I don't change the convergence property. Okay, so anyway, this thing here this is an example of what's called a geometric series. A geometric series has a fixed ratio between terms. So to go from 1 to 1 over 3, the ratio is 1 over 3. Another ratio of 1 over 3, 1 over 3, 1 over 3, so on and so on. All geometric series have that behavior as a common fixed ratio. And in general, it's written like this. A is the first term. In our example, A is 1. The next one is whatever the first number was, 1 in our example, multiplied by the common ratio, 1 over 3. Then AR squared is AR times another R. So it's the previous term times the ratio again. This is AR squared times R. So another one of these multiplied by R again, and so on. Okay? One nice thing about geometric series is it can have a finite sum that we can find precisely. So in other words, when you're encountering a geometric series, if certain conditions are met, we can find out that finite sum without doing that table, making a big long table and then find a limit. Okay, so let's look at how we can find these sums. So let me rewrite the series here. The condition has something to do with the common ratio. So for the moment here, let's look at what happens when R, the common ratio, is exactly equal to 1. If the common ratio is 1, then my partial sum, nth partial sum, is the first plus the second plus the third plus the fourth plus da da da. And I need to add up n of these things, right? And of course, that's just n times a, whatever the first term happens to be. And now, does this converge? Does this series here converge? Raise your hand if you say yes. Raise your hand if you say no. Okay, most people say no. Why not? How big can this get? As big as I want it to be, right? By adding as many terms as I want to. So if n is infinity, this thing blows up, right? So this clearly diverges. Stop. It diverges because if I take the limit of that, I get infinity. This number blows up. There is no fixed sum to that particular series when R is equal to 1, right? So clearly, R cannot be 1 for that series to converge. Okay, so let's stay away from 1 and see if we can find the sum. if r is not equal to 1, then the partial sum, the nth partial sum, is that. Do you see why the last term here has an exponent of n minus 1? Look at S3, for example. It's the sum of the first 3 terms. So it's A plus AR plus AR squared, right? So the nth partial sum, we add up to AR to the n minus 1. So make sense why this is n minus 1? Yep? Okay, good. Okay, so that's my nth partial sum. Notice what happens if I multiply both sides by r. If I multiply both sides by r, I get AR plus AR squared plus AR cubed plus dot 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 plus AR to the n. And now, let me subtract the first one. I'm sorry, let me subtract the second one from the first one. So first minus the second. And when we do that, what do we get? I get A, right? The AR is canceled. That minus that. That goes away with that. That goes away with that. And this continues until this guy here. So A stays, and the last one here stays. You see that? If you get confused putting a finite number for n, like S3, for example, you'll find out that S3 minus RS3 turns out to be exactly equal to that. We keep the first term and the very, very last one in the second series. Remember, I want to know the sum, so I want to know what Sn is equal to. So if I factor that out and then divide it by 1 minus r, then I get that. Okay, so that's my sum, provided that r is not equal to 1. Okay, then the question is that the only condition we have to meet? As long as r is not equal to 1, doesn't mean that this will converge. Think about that question. What do you think? Remember, that means that if I take the limit, then I cannot get infinity or minus infinity. What happens if r is equal to 2? What happens to r to the n as n gets large? It blows up, right? Same thing happens to r equal to minus 2. What about when r is equal to 1/2? What happens to r to the n? Eventually disappears. So where is that dividing line here? It has to be between 1 and minus 1. Good. So no. Converges only if it cannot be minus 1. It cannot be positive 1 either. Minus 1 has the same idea like that. 1, we already saw earlier, doesn't work. And very often you'll see it written this way. The absolute value of r is less than 1. Okay, now we're just one step away from finding the sum of any geometric series that has a ratio of less than, absolute value of ratio that's less than 1. If the absolute value is less than 1, then the limit of n goes to infinity of r to the n goes to 0, right? So this guy goes to 0. So therefore, the sum, which I'll use S for, to represent S, becomes A over 1 minus R. And I'm sure many of you have seen that formula before. Okay, so any geometric series with a common ratio of between -1 and +1 goes to that. Okay? Okay, let's try one example here. This one. If I add 6, 5, 25 over 6, 125 over 36, plus all of these things added together, what do I get? Okay, but the first thing you want to identify here is what the common ratio is. So what is it? 5 over 6, right? Right? 6 times that gives me a 5. 5 times that gives me this. This times that gives me that. And so on and so on. And what is A? What does A represent? The first term, which is 6, right? Okay, so that's simple now. The sum, which I can get exactly and precisely without doing a big long table, is equal to the first term divided by 1 minus the common ratio. And this turns out to be 36. Okay, no need to make a table, and we can be absolutely certain that that is the sum. Now look at this thing here again. Notice that for a series to converge, it was saying that eventually when we add these together, the number has to settle down somewhat, has to settle down around something. So, in other words, if a series converges, then the terms must eventually become very small. And that's the only way we can add up more and more of those, but still not exceeding a certain sum. Right? If they get smaller and smaller, eventually you're just adding more terms down, further and further down the decimal point. In other words, if a series converges, then eventually we must be adding up onto the sum something so small that's practically zero. Another way to establish this result Okay, remember earlier I wanted you to make a note of this result. Sn minus s to the n minus 1 is an. So that result comes in now. Right? So this is the limit of the n partial sum minus the n minus 1 partial sum. And now we know if the series converges, then the partial sum will eventually settle down to some finite number. What about the previous partial sum then? If the partial sum eventually go to s, what about the previous one? Look at this one we saw earlier. It eventually gets to 0.5. What about the previous one? Also roughly the same number, right? If you let n be large enough, which is what we're doing here. So this also goes to s. So therefore, what does that give me? And I get a 0, right? So this is saying that if the series converges, then the last term must eventually get to 0. Now, this is a very important point, this next point. This is a one-way statement. If series converges, the terms must eventually approach 0. The reverse is not true. If the terms approach 0, it does not mean the series converges. It does not guarantee convergence. All right, so be very, very careful with this result. If it converges, the terms eventually approach 0. But the reverse is entirely not true.